So we discussed the small signal behavior of differential pair last time, and we have identified the expression for the voltage wave. It was identified like minus Gm times RT. Now that particular expression that you have obtained last day was calculated based on some assumptions. The first assumption was that these two halves of this differential pair, this half, this left side and right side, these two are symmetrical in nature, right? That means these M1 and M2, these two MOS devices, they have the equal value of threshold voltage, they have the equal value of the transconductance, all the other parameters are equal, and then the tail current source that we have used over here, that tail current source was an ideal current source. So based on those assumptions, we have calculated the expression for the voltage gain, and it was obtained like minus Gm times RT. Okay, and you have also noticed that when both of these two gates of this MOS M1 and M2, they have the equal voltage value. That means if they are supplied with V in CM, constant voltage value, fixed value, then this V out 1 and V out 2, they are same, right? That means you have VDD minus, if I have this ISS over there, I have ISS over there going through this, then ISS by 2 in both of these two MOS, then VDD minus ISS by 2 times RT. V out 1 equal to V out 2 is equal to VDD minus ISS by 2 times RT. And accordingly, the output voltage was obtained with 0, the differential output voltage. That means the ideal differential pair, this is insensitive to the common mode variation. That means even if you have some common mode signal, and even if the common mode signal varies, you have the differential output that is a constant one, that is a 0. V out 1 minus V out 2, that is equal to 0. So that analysis we have performed with those assumptions that both of these two halves, they are symmetric in nature. This RT, you have these two drain resistances, they are also same, RT and RT over there, and this current source over here is an ideal current source. But suppose we incorporate some non-ideality into the structure. For example, suppose let's assume that both of these two MOS devices M1 and M2, they have unequal transconductance. For example, one is having a transconductance of GM1 is M1, and M2 is having a transconductance of GM2. They are not the same. And suppose the ideal current source that last time as a tail current source, that's not an ideal, and you have some non-infinite resistance over here. For ideal current source, you understand that resistance is infinite, right? But if you have some non-ideal current source, suppose a non-infinite resistance RSS present over here. So under this condition, even if both of these two MOS devices, M1 and M2, they are subjected to a common mode signal, that means this is not a differential signal because both the gates are tied together. Both the gates, G1 and G2, they are tied together. Some constant voltage V in CM. So ideally, you expect that V out 1, V out 2, they are same, and their difference equal to 0. But under this condition, with some non-ideality, we are interested in finding out what is the V out 1 minus V out 2, whether it is 0 or non-zero. If it is 0, that's fine. If it is non-zero, that means this circuit becomes sensitive to the common mode signal. So how to calculate this? So first of all, if I want to find out the drain current through this first MOS M1. So this drain current is nothing but this ID1. This drain current ID1 is GM1 times the gate source voltage. What is the gate source voltage? V in CM minus Vp. I call this point to point P. So gate voltage is V in CM, source voltage is Vp. So ID1 is equal to GM1 times V in CM minus Vp. Similarly, ID2 is equal to GM2 times V in CM minus Vp. And their summation ID1 plus ID2, their summation is equal to the current over here, that is ISS. So ID2 times RSS is equal to Vp. So you have two equations over here, and accordingly you can find out. So from this equation, you can find out what is the relation between V in CM and Vp. You just substitute over there ID1 plus ID2 into RSS is equal to Vp, and if you substitute those values of ID1 and ID2, then you represent Vp in terms of V in CM like this. Vp is coming out to be GM1 plus GM2 times RSS upon 1 plus GM1 plus GM2 times RSS into V in CM. That is the expression for Vp. If you just simply substitute the values for ID1 and ID2. Then what is your V out 1 minus V out 2? Let's find out what is V out 1 minus V out 2. Ideally it should be 0, but this time V out 1 minus V out 2 is nothing but minus ID1 minus ID2 times RT. Okay, and if you just simply substitute those values over here, then what you are getting is this V out1 minus V out2 is coming out to be minus GM1 minus GM2 times RT divided by 1 plus GM2 times RSS multiplied with VNCM. Last time your GM1 and GM2 they are same. So therefore, if I just follow this expression, last time GM1 and GM2 they are same. So therefore, this V out1 minus V out2 was equal to 0. But this time, since they are not same, they are unequal. So even if some VNCM is there, that means we are both of these two gates they are having some VNCM, some constant DC level. Then also you experience some change in the output level. I mean this V output minus V output is not equal to 0, but it is having a non-zero value, which value is given by this entire expression. That means the circuit is this time the circuit when the circuit is not symmetrical in nature. This time the circuit exhibits some sensitivity to the common mode signal. So even if the common mode signal is present, even if the differential signal is not present, still you find that the differential output is present. Now to the circuit, this particular thing, this particular output voltage V out1 minus V out2 is this can be regarded as the output due to the common mode signal only, because that output V out1 minus V out2 is due to the application of this VNCM. Due to the application of this VNCM. So what is the gain? So that gain is known as the common mode to differential mode gain. ACM, DM. Common mode to differential mode gain. Because you have applied the common mode signal VNCM. You did not apply any differential signal, you have applied the common mode signal, and in response to that, you have obtained some non-zero differential output. Right? So this ACM DM is nothing but this V out1 minus V out2, that is the differential output upon the common mode input. So here the output is differential and the input is common mode. And that expression is coming out to be minus GM1 minus GM2 times RT divided by 1 plus GM1 plus GM2 times RSS. Okay, that is the common mode differential mode gain, and ideally that gain should be 0. That means even if you have some common mode signal, the differential output should be 0. But since it is not a practice, since it is not an ideal situation, so therefore you have some non-zero ACM gain. And under this condition, we are interested in finding out what is the differential gain. Last time I calculated differential gain with the assumption that GM1 and GM2 they are same. But now we will do the same thing. We will once again repeat the same analysis, considering that GM1 and GM2 they are not the same. Okay, and then we will be finding out what is meant by the what will be the expression for the ADM. That means what is the differential mode gain. This is the common mode differential mode gain, and then we will be finding out what is the differential mode gain or differential output, differential gain. So for that, once again we will follow this same analysis that we have done last time, following this superposition law. So what I can get, first we apply V in 1 over here. So as you can see over here now, this time the applied input is a differential input. So if the V in 1 looks something like that, then V in 2 will look something like this. That is equal and opposite expression. Okay. So in order to finding out this V out1 minus V out2 upon V in 1 minus V in 2, let's apply this theory of superposition one after another. So first we assume that V in 1 is acting alone, and let's find out what is V out1, what is V out2. So if V in 1 is acting alone, that means this gate, this M2 is having a 0 input at its gate. So V in 1 is applied only. So under this case, what will be the expression for your output voltage? I mean V out1 upon V in 1 is once again common source with degeneration. But what is the degeneration resistance? So now this time you have, this was infinite, right? So you don't have any current flow through this last time. But this time you have this resistance along with that resistance, right? So this RSS and that 1 upon GM2. Last time I calculated 1 upon GM2. Apart from that, you have this RSS. So these two are coming in parallel. So now this is your degeneration resistance, RSS parallel 1 upon GM2, right? So then what is V out 1 upon V in 1? So this V out 1 upon V in 1 is minus the resistance between the drain and the AC ground, that is RT. So we have neglected this R naught over there. So minus RT divided by 1 by divided by 1 by the transconductance of the amplifying device plus the resistance seen between the source and the AC ground, that is 1 upon GM2 parallel RSS. And if you simplify this one, then V out 1 upon V in 1 is coming out to be this one. If we simplify this expression, okay, then we will be finding out V out 2 upon V in 1, right? So what is the formula? So for that, so last time almost the same circuit. The only difference is that last time you don't have this RSS over here because that was infinite. So we have this Thevenin equivalent model V in 1, 1 upon GM1, and this RSS was absent. It was an infinite resistance, so open circuit basically. So this time RSS is present, so the voltage that is applicable over here, Vp, so we can directly calculate this one. Is nothing but V1 upon RSS plus 1 by GM1 multiplied with RSS, right? That voltage Vp. So you can represent Vp in terms of V1, and what will be the effective resistance if I consider over here this effective resistance is nothing but 1 upon GM1 parallel RSS, right? Then what is V out 2 upon Vp? This V out 2 upon Vp is given by RT upon 1 by GM2 plus this RP. So if you simplify this one, then this is the expression V out 2 upon Vp. So we have got V out 2 upon Vp, and we are interested in finding out V out 2 upon V in 1. We already got Vp upon V in 1, that expression. So your V out 2 upon V in 1 is nothing but V out 2 upon Vp multiplied with Vp upon V in 1. So if you simply substitute those values, then what you get is this expression. GM1 GM2 RSS RT upon 1 plus GM1 plus GM2 RSS. That is the expression for V out. So you already got V out 1 upon V in 1, and this time V out 2 upon V, right? So when both of, when you are calculating this V out 1 minus V out 2 upon V in 1 is nothing but the summation of each of these. So what is that? So you have got this one, V out 1 upon V in 1 is minus GM1, this big expression that you have got. This one, V out 1 upon V in 1, and this time we have got V out 2 upon V in 1, this expression. Okay? So what is V out 1 minus V out 2 upon V in 1? Just the algebraic summation. So that one. So V out 1 minus V out 2 upon V in 1. That is okay. V out 1 minus V out 2 upon V in 1 is minus GM1 RT plus twice GM1 GM2 RSS RT upon 1 plus GM1 plus GM2 RSS. That's fine. Then suppose V into is applied. Right. This time remember that GM1 and GM2 are different. So whenever you find GM1 in the expression, replace by GM2, and whenever you get GM2 in the expression, that has to replace by GM1. And if you have minus sign, that should be replaced by plus. Right? So what is V out 1 minus V out 2 upon V into? So we have minus over there, so that should be plus. This GM1 is replaced by GM2. Twice GM1 GM2 RSS RT will remain as it is, and 1 plus GM1 plus GM2 RSS will remain as it is. Right? Now remember what is V1, what is the relation between V1 and V2? V1 is basically the opposite of V2. So if you now calculate the mod of this gain and mod of this gain, these two gains should be the same, mod wise, right? So if I call this mod as AV, then this one must be the same. So mod of V out 1 minus V out 2 upon V1 must be equal to mod 1 minus V out 2 upon V2. And let me call this as mod AV. So mod AV is given by this one, GM1 RT plus twice GM1 GM2 RSS RT upon this entire thing. And that is also equal to GM2 RT plus twice GM1 GM2 RSS RT divided by this entire thing. Right? These two are same, mod AV. These two are same because mod AV is equal to this, is equal to this. Mod, I am just mentioning the mod. Where? I am just mentioning the mod, modulus. No. Here you have GM2, here you have GM1, so this GM1 is replaced by GM2. Whenever you find GM1, that should be replaced by GM2 because it is calculated with respect to V in 2. That's why. No, I'm coming to that. Right? This is equal to this. Right? So if you add now, so mod AV is equal to this, mod AV is equal to this. So what is 2 of mod AV? This plus this. Okay? 2 of mod AV, just add them. So what is mod AV then? What is mod AV then? 2 of mod AV is equal to, if you just add them together, this expression, so you just add this expression. This is mod AV. This is also mod AV. So we add them. This plus this. This plus this is equal to 2 mod AV. What is that? The numerator being denominator being the same, 1 plus GM1 plus GM2 RSS, and if you add the numerator, GM1 plus GM2 RT plus 4 GM1 GM2 RSS RT. That is twice mod AP. Okay, then what is mod AP? And that's nothing but the differential mod ADM, because we have applied the differential input. So what is this mod ADM? This mod ADM is mod AP. If you just divide it by 2, then what is that? RT upon 2, GM1 plus GM2 plus 4 GM1 GM2 RSS plus 1 plus GM1 plus GM2 RSS. That is a entire expression for mod AP or mod ADM. That is the differential mod gain, right? With GM1 not equal to GM. Now, once again, I have to consider, okay, in this expression, let GM1 is equal to GM2 is equal to GM. Let's assume that these two are same. Then, obviously, you will reach to the same expression that you have already got. What is that? Mod AP is equal to this time. Although that time RSS was not there, RSS you will find it anyway. If we just substitute this one, what is that? RT upon 2, GM1 GM2, that means 2 GM plus 4 GM square RSS upon 1 plus 2 GM RSS, right? RSS. That can be written like already here, and you have GM plus 2 GM square RSS upon 1 plus 2 GM RSS. You are not familiar with this expression because that time RSS was also infinite. We made two changes. One change in the form of GM1 is not equal to GM2. The second change in the form of RSS is not equal to infinite. You are familiar with GM1 equal to GM2 is equal to GM and RSS is equal to infinite. What was the gain? The gain was GMRT. Mod of gain was GMRT. Now, GM square RSS by 1 plus 2 GM RSS. Now if you make RSS equal to infinite, this is nothing but 2 GM square by 2 GM. That is simply GM. GM times RT, mod of this GM times RT. So you have got the same with this assumption that GM1 is equal to GM2 is equal to GM and RSS is equal to infinite. Anyway, for generic calculation, this is the expression for your differential mode gain ADM. And already we have got what is the expression for? Already we have expression for your ACM DM, that means common mode to differential mode gain. We have already got this one last time. This is the common mode to differential mode gain, ACM DM. This one minus GM1 minus GM2 upon RT multiplied with RT divided by 1 plus GM1 plus GM2 RSS. So now we are in the process of getting the common mode rejection ratio, CMR, the ratio between these. We have got ADM. ADM was given by RT by 2. That expression, that big expression that we have got right now. This one ADM, and this one is ACM DM, common mode to differential mode gain. This one, right? What is the CMRR, common mode rejection ratio? The ratio of these two. So the denominator gets cancelled here. In the numerator you have GM1 plus GM2 plus 4 GM1 GM2 RSS upon twice GM1 minus GM2. Now if GM1 equal to GM2, then obviously in that case the common mode rejection ratio is becoming infinite. And that is for an ideal differential amplifier you expect that the CMRR should be infinite. Practically this CMRR is not equal to infinite but very large. As you know, for the op amp also, you know that the CMRR is very large, but it's not equal to infinite. Ideally it should be infinite, but practically it is very large. So the expression for this CMRR, in many of the books you will find the final expression for the CMRR. If you just follow this book by Behzad Rezavi, there also you will be getting that final expression for CMRR given by GM1 plus GM2 plus 4 GM1 GM2 RSS upon twice GM1 minus GM2. That is the final expression. But the process of calculation and how to find out the CMRR, the ratio of these two. So this process has been elaborated over there, and this is the final expression for your CMRR. That means common mode rejection ratio. Okay. So as of now, what we have done in differential amplifier, we have discussed what is made by the differential signal, what is made by the differential amplifier, the last signal characteristics of differential amplifier, and then comes the small signal analysis. And in the small signal analysis, we have categorically assumed that the resistance, the drain resistance, was basically one discrete resistance in the form of RT. But in your, we have discussed the the common source amplifier, common gate amplifier, common drain amplifier in the last unit, hopefully you have noticed that typically this resistance can be replaced by some other loads. For example, you can have the current source load, you can have the direct connected load, and each and every of these loads, they are having their own advantage and disadvantage. Apart from that, it's RT, we consider this RT. And typically here in the sector analysis, we have considered that RT. I mean, we have used a simple resistor. But as you know, this resistor can also be replaced, but has to be replaced because if you just simply use a resistor, it is having its own limitations. So you do the same thing. That means once again, this analysis has been done. Now for a simple differential amplifier with a resistive load, now what we can do, we can simply substitute that resistor by means of some other types of loads, and let us see what is the advantage that we are getting out of this. Differential pair with what kind of load? Direct connected load. So what is the advantage of direct connected load? As of now, you have seen that the gain was minus GM10 factor. Right. What is the problem associated with that? No. What is the problem associated with this GM minus GMRT or whatever, something like this? What was the problem associated with that? The problem is that this GMRT or minus GMRT, that particular gain is not a stable one. It's a function of temperature, it's a function of bias current. So we are in the process of making the gain of this differential pair a stable one. How can we do that? You have noticed that if you can replace that resistor by means of direct connected device, for a direct connected device, as you know, the impedance is given by 1 upon GM. Right. So therefore, what we find, so this M1, M2, they will form the amplifier pair. M1, M2, they will form the amplifier pair. And this M3, M4, they will form the load pair. Right? And what kind of load? It's a direct connected load. So gate and drain, they are shorted together. So this is the source terminal for PMOS. This is the source terminal for the PMOS, so that you don't have the body effect to consider. The source is connected to VDD, and gate and drain, they are shorted, right? Gate and drain, they are shorted. Now, if you have a ideal current source over here, then you can invoke the notion of this half circuit concept. You can invoke this one. So ideally, this is a ground, this point is a DC ground. Then this half part of this circuit can be represented like this. We have VDD there, M3, this load resistor as a direct connected load, and you have this M1. Okay, what is the gain? So this M3 is represented by 1 upon GM3 parallel RO3. If I consider this RO3 of this particular device, it's 1 upon GM3 parallel RO3. That will be the resistance provided by this direct connected device. And here you have, this is basically a common source kind of thing. Common source amplifiers. What will be the effective overall gain? This is minus GM1 multiplied with 1 upon GM3 upon 1 upon GM3 parallel RO3. Right. So that will be the expression for the gain. AB is equal to minus GM1 and then multiplied with 1 upon GM3 parallel RO3, and obviously you have to consider this RO1 of this particular MOS. So 1 upon GM3 parallel RO3 parallel RO1, because these are the three resistances which are connected between this drain terminal to AC ground. So 1 upon RO1 over here from drain to source for this M1 for this amplifying device, and 1 upon GM3 parallel RO3 for this particular device M3. Typically, this 1 upon GM3 will dominate in this parallel combination. So ultimately, this is almost equal to minus GM1 upon GM3. Right?
Ideal current source is the one kind of MOS device.
Which?
Ideal current source because the one kind of MOS device.
In that case, if it is not an ideal one, suppose you are representing this one by, okay, we will discuss. Suppose this ISS is not an ideal one. Suppose you have some MOS device for this. For example, like something like this. The current source, right? I can represent current source using NMOS here. Yes. So with some voltage, say let it be say VB, and suppose this is your MOS M5. So obviously it is an ideal. So it's not an ideal. It's not an ideal. You have some RO. We have some RO. Typically, you have some RO. You have some RO. RO there from. I mean, there you have some RO from. I mean, this is equivalent to having some RO. RO5 corresponding to the output resistance of this current source. So that is the differential, right? So okay, in this particular case we have just neglected that. Anyway, so the gain is minus GM1 upon GM3, right? So gain is stable. Why stable? Because minus GM1 upon GM3. I think this is there in the next slide, so we can move. Yes. So yeah, the same current is flowing through this 1 and 3. Through 1 and 3 you have the same current. So what is your GM expression? You know that GM expression is given by twice mu and C of W over L by square. So if I assume that both of them are sharing same mu and same C of, then obviously same ID, same kind is flowing through this M1 and 3 combination. So ultimately it's nothing but the ratio of this mu n square root of mu n W by Ln upon mu p W by Lp. Typically, this mu n, as you know, the mobility of electron is higher as compared to the mobility of the holes. So let it be this ratio of, let it be say 10 times or 20 times. So obviously now if you select that okay W by Ln and W by Lp they are same, the aspect ratio of this NMOS and aspect of the PMOS if they are almost same, then ultimately this voltage gain is governed by minus of square root upon mu n upon mu p, and that is not very large. Now suppose you would like to make this voltage gain, I mean obviously one of the objective is to make the voltage gain stable. At the same time, it should be, I mean, the voltage gain should be large and stable. Again, stable, right? So for the stability, you have used this diagram for the stability. But for increasing the gain, what you need to do? Because you don't have any control over this mu n upon mu k. This is not under your control. So what you can do, you can have some, I mean, you can play with this W by Ln upon W by Lp calculation. So what you can do, you can obviously you cannot increase because since your objective is the compact design, so you cannot increase in W by L or you cannot increase the weight. That is not your botheration. You have to reduce something so that the circuit is becoming much more compact. So you cannot increase W by Ln. Rather, what you can do, you can reduce this W by Lp. Right. Now, if you make any attempt to reduce W by Lp, then what is the penalty that I have? In order to increase this voltage gain, you have to reduce this W by Lp. Right. But remember, the current is constant. You have some constant current source, so current is constant. You can't have high current through this. So now, if I equate the current in the NMOS and the PMOS, you have the same current now. The current which is flowing through this, you have the same current flowing through this. So M1 and M3 they have the same current, and they are in the saturation. Now, what I can write like this. So in the saturation, half mu n C of W by Ln VGS minus VTH n whole square is equal to half mu PCX W L P VGS minus VTH P whole square. They have the same current, right? Now, okay, mu n Cox, mu P Cox, okay, that is fine. Now, we have some fixed current. Current is fixed, constant current, for example. Now, for increasing gain, what you need to do? You need to reduce this W by Lp. Right? You have fixed current. You have to reduce this W by Lp. What is the penalty? You have to increase this one, VGS minus VTH whole square, VGS minus VTH P whole square. You have to increase this one. So what if, now if this is increased, what is the penalty we are paying? Gate to source minus threshold, that means the overdrive voltage. For PMOS, this overdrive voltage is increased. That means you have that the less swing. You have less swing available. Okay, you can have high gain, you can have stable gain, but at the cost of what? At the cost of the allowable swing. That is restricted, right? That is sorry. That is one problem. And second problem is, okay, so this problem can also be addressed. This can also be arrested by something. Then your circuit becomes even more complicated. Started with a simple differential amplifier with a resistive load. You know that the gain is minus GM1T. Now, in order to make the gain stable, what you have to use some direct current so that the expression is minus GM1 upon GM2. That's a stable, but it's not that large gain. In order to increase the gain, what you need to do? You have to reduce W by Lp. for which you have to increase this overdrive voltage of the PMOS, and that will restrict the available swing. Right? Now suppose I would like to have all these three features, like I would like to have a high gain, stable gain, and at the same time the swing is also not restricted. Right? So what do you need to do? So what is the bottleneck here? I can reduce W by LP, but if the current is fixed, fixed current, suppose say for example, I am having say ISS is equal to 1 milliampere. For example, ISS is equal to say 1 milliampere. That is the bias current. So this M1 and M3, M1 IM1 is equal to IM3. That means the drain current flowing through this is nothing but 0.5 milliampere under DC condition. 0.5 milliampere only. Okay. Now with this, so this 0.5 milliampere is equal to this much. 0.5 milliampere is equal to this much. So now if you make this one smaller, or if you want to have some mechanism so that W by LP is smaller with a given IM3, that has to be increased. Now I would like to have something, I would like to devise some mechanism so that this W by LP is reduced, but this is not also increased to that extent. What is the way out? I mean, this is equal to 0.5, na? This is equal to 0.5 milliampere. Where to connect? No, not in series. Not in series. Why not in series? Because now this one is, I mean, they are sharing 0.5 milliampere current. This is equal to 0.5 milliampere, right? 0.5 milliampere. Now suppose you would like to minimize this one WLP, so that will increase. This one will increase. Now what I want that okay, WLP has to be reduced, but and if WLP is reduced, obviously that will also increase, but it will not increase to that extent. So what I can do, I cannot allow this entire drain current of M1, this IM1, I don't want to have this entire drain current of M1 to flow through this direct connected load, but a portion of this to flow through this direct connected load. So this kind has to be shared, needs to be shared, and needs to be shared by means of another, say, current source. I need another current source in parallel, which will share this drain current of the MOS M1. Okay. Yes, so what is my device structure? Let there be 50% sharing. Okay. Suppose there is 50% sharing like this. 50% sharing. So this is basically the amplifying MOS M1, M2. Right? This time you have this one is the direct connected device M4, and now you have this M3 is acting as a current source. Previously, now if I call, suppose this current is equal to, let it be say I1, let it be I1. This current. Previously, this I1 was carried by M4, I mean this direct connected device only, M4 only, previously. Now this time, when you modify the circuit like this, so 50% of this I1 will be carried by M4 and the rest 50% will be carried by this M3. No, you can have different percentage. You can have 50%, 50%. Now that depends on what is the bias you have provided for him. No, what bias you are providing here? This is acting as a current source. So obviously you know what is the current here, what is the total current here. This current is how much? I1 times I mean this I1 is how much? This by 2. This IC by 2 is equal to I1, and based on I would like to have 50% of I1 to flow through this M3, and accordingly you have to select the VV value. This VV value will determine how much current is flowing through this M3, and that percentage you have to calculate. What is that percentage, right? So for a given VV, suppose it is sharing 50% of that. So it can be 60, 40, 70, 30 minutes. But the bottom line is that at least a portion of the current has to be shared by some other current source. Not this entire current will flow through this M2. So that what happens now? Now you know this is the expression for GM, square root of twice mu n C ox W over N times ID. Right? Now here, if you reduce W by L by 4 times, W by L by 4 times, by a factor of 4. Here, if we consider this, if W by L is reduced by a factor of 4, then GM will reduce by a factor of 2. No, for any GM, if you just consider, suppose W by L4 is W by L is reduced by a factor of 4. If I govern this, if I consider this particular expression, then GM will be reduced by a factor of 2. Right? Now here what we are doing, if I have this 50% current flowing through this, because now this time what we have, this is the scenario for the last case, previous case. That means we have the same current. That means this ID is basically the I1. This ID is basically this I1. This is equal to, this ID is equal to I1. That time you don't have any current source in parallel with this dark magnetics. Okay. Now what we are doing, this time this ID is itself reduced by 2 times. ID is itself reduced by 2 times because now you don't have this complete I1 flowing through this M4. Rather I1 by 2. I1 by 2 is flowing through this M4. Right? So therefore, in order to reduce GM by a factor of 2, what do we need to do? This W by L has to be reduced by only a factor of 2. Right? W by L reduced by a factor of 2, ID is reduced by a factor of 2, so that GM will reduce by a factor of 2. Now, if W by L is reduced by a factor of 2, go to that expression. In order to keep this VGS minus VT, in order to keep the current constant, this VGS minus VTHP will increase by a factor of root 1.414. But this time, if WL is reduced by a factor of 4, then this VGS minus VTH will increase by a factor of 2. So in one case, in one case, the overdrive voltage will it is not reduced; it should be increased. It should be increased, right? So in one case, your overdrive voltage is reduced by a factor of 1.4, and in the last case, the overdrive voltage was increased by a factor of 2. So that is not at all desirable. You like to reduce the this enhancement of this overdrive voltage. So if you have this particular kind of thing, that means if the current is being shared by another current source, in that case you can have the stability, at the same time the gain is also increased, but at the same time the penalty is not there in terms of your available swing. That is at this particular output terminal. Right? And then finally, I think there is another slide to complete this discussion on differential amplifier. So I think, another slide is there. And finally, the gain can also be increased further. But still, so that is one approach. That is one approach using this diagonal load. And the final approach is that, so suppose you would like to increase the gain as high as possible. What is the way out? You can use what kind of load you have to use for this, so that the gain is very large, tremendously large. You have to replace RD by something. What is that something? What is that something? That is nothing but a current source. Simple current source. Simple current source. For current source, what is the output? R0. That is large or 1 upon G. Right. Oh, this is the penultimate slide. There's another slide after that. So this time you have now this time you are not bothered about this stability. You are bothered about the current. You are bothered about the gain only. Right. So that's why what we have done this time you have this load is represented by the current source, right? And you know for the current source, the corresponding the resistance is given by simply R03 here and R04 there, right? So therefore, if I once again it concept, then what is your overall voltage gain? This is nothing but, so here you have half circuit is represented by this one, this M1 there, which is acting as the amplifying mass, and M3 is acting as the load mass, acting as a current source load. Okay, so for this one, what is the resistance from here to here? This is RON, N, and here from here to here you have ROP. So minus GMN multiplied with RON parallel ROP. Right? That means you can increase the voltage, but still also stable because we have GM so these are dependent on the temperature. So V is equal to minus GMN multiplied with RON parallel ROP. Right? So current source. So we have discussed the direct connected load, then the current source, and then we have also studied that okay, fine. For current source load, the output resistance, the resistance is given by RO. RO is the output resistance for current source. Now, suppose you would like to increase the resistance even more, degenerate, or you can go for a cascade kind of cascade. For cascade configuration, what was the effective output resistance? 1 plus GM RO times RS plus RO. So, yeah, that is the final thing. Yes. So this time, both the amplifying part and as well as the load part, you have a cascade kind of thing. So let me explain. This is the final slide. So let me explain. Previously, what you have seen only one MOS. One MOS amplifies one MOS in the one side only. One MOS is suppose this one was acting as amplifying MOS and this one is acting as the load MOS. Right. Now this time, what we are doing? The actual input is applied over here, Vin is applied over here, right? It's a common source because the input is applied at the gate. Common source amplifier, and then you have this output is given to the source of this MOS. So this MOS is acting as a common gate amplifier because the gate is at a constant potential, Vin. So common source, common gate, cascade, that is nothing but a cascade amplifier. Common source, common gate, cascade is a cascade amplifier, right? Similarly, if you consider here, so here you have this particular thing. This is basically, what is that? This one. This is a single current source, but this current source, this is the source, this is source, this is the drain, and then here you have this kind of connection. So it's a cascade connection. This M5 M7 is a cascade connection. Similarly, M6 M8 is a cascade connection. So for cascade, what is the output resistance? Typically, here you find that for this one, you must the body effect for M5. Similarly for M3, we will explain the body effect because for M5 and M3, their sources are not connected to the respective terminals. For M3, you should expect that the source should be connected to the ground. For M5, you should expect the source should be connected to the power supply. That is not the case. So they will experience the corresponding body effect. Right. So what will be the output resistance here? For example, if I just consider this only M3, you understand that this is nothing but what will be the corresponding output resistance looking from this terminal to ground, from here to here. What is the output resistance for this cascade? This is basically cascade amplifier. Common source followed by common gate. So what is the effective output resistance from this terminal to this terminal? This is nothing but 1 plus GM3 plus GMB3 times R3 multiplied with R1 plus R3. That is the expression, and that can be simplified to GM3 R3 R1. Typically GMB3 can be neglected, and this plus can be neglected, plus R3 can be neglected. You just consider the product term GM3 R3 R1. Right, GM3 R3 R1. So therefore, for this case, so that is the scenario for this amplifying part, and load part is also cascaded. Amplifying part and the load part, both of them are cascaded, right? Then what you get here? There you find this is the amplifying MOS. This is amplifying MOS, and then you have the corresponding resistance between this terminal and AC ground VDD, and this terminal and AC ground. What is that? Minus GM1. If you just consider the modulus, so GM1 And with this substitution or with this approximation GMT RO3 RO1, so here you have GMT RO3 RO1 for this side, amplifying side, and this is coming in parallel with this side. What is that? GM5 RO5 RO7. So GMT, so there is an approximation. There is an approximation. We have just neglected the body effect. Otherwise, the actual calculation will be something like that: G1 plus GM3 plus GM3 to RO3 plus RO multiplied with R1 plus RO3. Anyway, but with some approximation that can be regarded as GM3 RO3 RO1. So basically, what we have between here to here, you have this one, and between here to here. So this side is also at DC ground. Right? And accordingly, you have to find out what is the, so here you have for this GM3, RO3, RO1, and there you have GM5, RO5, RO7. So parallel combination of these two, and ultimately that will be the expression for the voltage. So there, so finally, before I conclude this lecture on differential amplifier, so I have also given you some flavor regarding how to use the different types of loads. Not only the differential, not only the resistive load, only RD, but other types of load like that we already studied in the unit 3, like the direct connected load, the current source load, the combination of them, and as well as the cascade load, and obviously the input side is also in the form of cascade, so that the gain can be enhanced. Typically, what you have seen previously, the gain was like GM10 30. This time the gain is something like that, GM1. Then the product of this, product of GM RO, 2 RO, and GM. So ultimately, what is that? So ultimately, this mod AP can be approximately like in the form of GM RO whole square. Almost, because we have GM3 RO3 RO1 parallel GM5 RO5 RO7. So their parallel combination is in the form of GM RO 1 GM and 2 RO, and this is multiplied with another GM. So GM RO whole square. So obviously this is much larger as compared to your previously obtained GMRT. This one is larger. But you may argue that this is not stable. This is not stable, obviously. For stability, you can refer to that particular configuration where we have used this direct connected load and in parallel with another current source. Okay, fine. So with this, we have come to the conclusion of this differential amplifier, both the large signal as well as the small signal analysis.